Garden at Columbia, Yanjan at NYU, and Kunha was a grad student at Berkeley. The setup of the talk, or the thing that we are mostly interested in, is sequential decision making. To this audience, I don't need to say why, at least in the modern day, sequential decision making has become really important. Questions like applications like self-driving cars, repeated games, data-driven algorithm design, repeated randomized control trials, inventory management, and now even like algorithm design have all been sort of addressed using the framework of sequential decision making. So the question that we want to understand is the complexity of sequential decision making, both statistically and computationally. So today we'll focus on a very particular formalization of sequential decision making, which is supposed to be the prototypical example. So we'll focus on a particular case, and we'll see that the tools that we'll develop are somewhat more general. So here's the setup. It's called sequential binary prediction. And first we look at the stochastic case. So in this setup, there are two agents. One agent known as the learner, and the other agent, which is the environment, the adversary, or nature. But we'll for different like aspects of this. But in the stochastic case, we'll have nature. And at each time step, there's a fixed distribution d, and at each time step, thank you. Oh no. At each time step, xt is sampled from this distribution, and the learner sees this. The learner then makes a prediction y hat t, which is binary, sends it to nature, and then nature tells the true label yt. So what you're trying to compete against is a set of hypothesis f, which is called a hypothesis class, and we want to do as well as the best hypothesis in this class on the given data. How do we measure this? The standard notion is called regret. This is defined to be the loss of the learner, which is the number of mistakes that the learner makes on the data, which is the number of times yt is not equal to y hat t, compared with the best hypothesis in hindsight. That is the number of mistakes the best hypothesis makes on the data, looking at xt in hindsight, like after the data is realized. So this notion is known as regret. This is a very standard notion, which, for example, the most place that most people see this is something called the experts framework, and this is a slight generalization of that. Yes.
Is there any expectation?
Oh yeah, sorry. Being sort of sloppy with like probability. So your algorithm is allowed to be randomized, and like in this setup, the xt is also randomized. So there's an expectation outside, like that's an expectation here on the whole transcript of like the probability over all the randomness of the word. Does that make sense? So this is a stochastic setting. The most sort of familiar setting is the adversarial setting, where again you have a learner, and now you have an adversary who gives you an xt, which is arbitrary, with no probability assumptions on xt. Gives it to the learner. The learner again gives a y hat t, again binary, and sends it across, and the adversary gives you a true label. Again, you want to compete against a set of hypotheses, and the regret again is measured in terms of the loss of the learner compared to the loss of the best adversary, best action in hindsight. Yes.
Do we consider any particular class of hypotheses or others?
For now, let's think of it as abstract. We'll see that to get anything meaningful, you'll need to sort of like you'll get some parameterized quantity in terms of the hypothesis where you can get like regret bounds. But for now, it's literally a set of like it's an arbitrary hypergraph. Are there any other questions? Okay, so that's good. That's the definition. So one issue with this adversarial notion of learning is that for even simple settings, you can't achieve any non-trivial guarantees. The problem is actually somewhat easy to see. Here's a toy thing that can go wrong. So you have a decision maker. At each time, he needs to decide whether to go left or right. So in the first round, he says, "Okay, let me go left." The learner, the adversary then says, "Okay, no, you actually have to go right." You continue with this. Now the learner says, "Let's go right," but the adversary says, "No, you actually had to go left." this goes on. The adversary says left. You go. You actually had to go right. It seems like maybe the reason why you're doing making so many mistakes is because the thing that you're competing against is very complicated. But unfortunately, in this setting, the thing that there's a simple hypothesis in hindsight, which is just a simple threshold that actually would fit the data exactly. So you'd get no non-trivial guarantees. We'll get back to something similar later. So okay, now we look at the actual complexity of sequential prediction. So in the stochastic case, this is actually the most well-studied classical case, back to like Vapnik, Chernovinkis, and say Valiant. You can show that the regret is bounded by t times the VC dimension. If you're not familiar with the VC dimension, it's okay. For this talk, you can think of this as a small number. And in the adversarial setting, you also have a corresponding characterization, but this time it's in terms of some other quantity called the Littlestone dimension of the hypothesis class. And the unfortunate thing is the Littlestone dimension is infinite for any class that you can essentially any class you can talk about. In particular, any class that contains a set of one-dimensional thresholds. That is, set of indicators for, like, let's say greater than x, like the set of functions that are the indicators of greater than x on even in one dimension, that has infinite Littlestone dimension. So yes. Yeah. So okay, good question. So this VC dimension dependence is uniform over all distributions. So you give any distribution and you get this regret bound. You could ask for like distribution dependent bounds. Those are known. This is actually fairly well in the stochastic case. All of these was fairly well understood. We can talk about it offline, but like this is a uniform bound for any distribution. So it's the packed model. Yes, oh yeah, sorry. When I say regret, I just mean expected regret. Unless yes.
I'm guessing the class F is non-finite. So, can you characterize LD? Like, how do you get that?
So depends on as in what the definition is. It's a little annoying, but it's roughly like I showed the tree example, right? It corresponds to the largest depth of a tree that you can what's called shatter with the class. So it's some definition. It's actually fair. Once you see the definition, it's actually somewhat easy to see that it characterizes online learning. It's very similar to the VC dimension definition if you've seen it before. Like VC dimension says it's the largest set that you shatter. In this sequential setting, you'll have to shatter trees. We can get back to this. It's not super important to know the definition. Yeah.
In the car case, it's just the number of moves.
Number of moves that disagree with. Is that any other question? Okay. So, right. So that quantity is infinity. So the regret you get is like essentially infinite. Sorry, I mean like trivial. So you'll get like t regret or something like that. Yeah, and you can also ask about the computational complexity of this problem. The computational complexity of the stochastic case turns out to be related to this notion called empirical risk minimization. The only thing you need to do is look at the data you have seen so far and fit the best hypothesis on the data. This predicting using that is will give you the good regret bounds. This problem itself could be hard, but like you are actually dealing with average case inputs and many sort of real world scenarios, you could have heuristics like neural networks or like gradient descent, which tend to work. Yes.
So that regret bound is tight as well.
So it's min-max optimal in the sense that there is for each hypothesis there's a set of there's a distribution. Okay. So like Chandan asked, you could get like distribution dependent rates if you wanted to. So this bound is min-max optimal in the sense there is a distribution. Any other questions? Okay, so that's good. Now the thing to compare this to is the adversarial online setting. Here, even if you knew how to do empirical risk minimization, that is given a data, if you could fit the best hypothesis, even if you could do that, you can show a query complexity lower bounds that show that you can't even in polynomial time you can't get non-trivial regret, even given Oracle access to empirical risk minimization. So this is a hard, like it's a information theoretic lower bound, like it's a query complexity lower bound, not a like computational lower bound. So in some sense, this that problem is objectively harder than this problem in some interpretation of those words.
Yeah. So to clarify, there might be 2-3 notions of regret. So cumulative, min-max, simple regret. This would be min-max.
I mean, this would be like what would be called external regret or something like that. Like it's. Oh, I don't know what you mean by min-max regret, but
you just mentioned.
Oh, sorry. So that's okay. What I mean by min-max optimal is that it's if you like maximize over all hypotheses, like take an algorithm, then maximize over all distributions. That quantity, that min-max, the regret is inside, and then you maximize over the thing. That would be like. Does that make sense? Okay, so why look at these two different notions? One thing about like the stochastic case is that it gives you clean statistical rates. Learning reduces to optimization, which maybe we know how to do, and it's in many different settings. This is a good uh, model for learning. But the issue is that this is an extremely strong modeling assumption on the world. You are assuming the data is IID every today looks like tomorrow, which somehow loses something fundamental about sequential decision making. And it's not robust to corruptions or manipulations just because you have like you need to assume that the data is IID. The adversarial setting is great for whenever you had the constant the stochastic setting, which is that you are making essentially no assumption on data, and you're capturing correlations between the past and the future, which is somehow important for like sequential decision making, and it's by definition robust to adversarial corruptions because you're making no assumptions on the adversary. But unfortunately, both statistically and computationally, you can't get any guarantees in this setting, and by default, at least, it does not incorporate structure about the data, and in some sense, it's overly pessimistic. So the main question that we want to sort of talk about is whether we can bridge between the two worlds to get maybe get the best of both worlds.
So in the stochastic case, several assumptions can be made, like distribution. The adversarial side, can any assumptions be made?
Yeah. So I mean, it's a whole thing. So we'll talk about one version of that, like one. So the whole talk is about like a certain assumption on the adversarial case that will give you essentially the best of both worlds. But there are like in different settings there are different things people talk about, and you can get like it's actually a fairly rich area of study where this beyond worst case setting for even the adversarial setting. Yeah, so we'll talk about like one version of that. Yeah. The D is fixed and then XT is fixed. But you see XT at time, like the most standard patterning is you'll be given all the data up front and you fit your model and then get tested on new thing. Here you're getting data sequentially, but it's still like it's sequential prediction, but it's still the data is assumed to be IID. And yeah. Yeah, so in the adversarial setting, XT can depend on everything that XT plus 1 can depend on everything that has happened in the game till time till time t. So in particular, XT and XT plus 1 are like correlated random variables, where like the randomness is over all the transcript till time t. But in this, in the stochastic case, XT is independent of everything you've seen so far. Any other questions? Okay, so what we want to do, as like a great question was asked, like are there assumptions or are there reasonable things that you can say about the adversarial case to get bounds back? And to do this, maybe let's recall all the applications that we had in mind before, and what is the thing that we want to capture? And the thing that we want to really capture and not miss out on is the dependence of future instances on the past data and on the actions of the adversary. So in some sense, you want like to capture settings where the data for tomorrow depends on everything you've seen so far. This is really important in like stateful systems, which many of these are, when the decisions you make and the current this thing does affect whatever happens tomorrow. So this is one thing you want to capture. And the IID does not capture this, and therefore maybe it's not a good assumption. The other thing, the other property of the data that you might want to take advantage of is that the samples are inherently noisy, and you should not expect the examples that you're seeing in real life to be arbitrarily badly specified and, for example, have arbitrary bit precision in its description. So you want to say that there is some noise in the thing that you're predicting on. The ideal goal is to come up with a model that captures the properties, these properties of the real world, while also getting bounds similar to the stochastic settings.
So could it be possible that so you're talking about correlation between xt plus 1, let's say x0 to xt and xt plus 1. So it might be possible that the adversary tries to minimize this correlation.
I mean,
that might be one of the goals.
Goals of the adversary? Yeah. Sorry, maybe I didn't understand.
So the adversary can give any xt plus 1.
Yeah.
And let's say they try to minimize the correlation.
Okay.
So would it still? So could you still use correlation? So
maybe I don't understand.
What would you mean by correlation?
Oh, I mean, I just mean it in the probabilistic sense, in this the conditional distribution of xt conditional on xt minus 1 is how different is it from the unconditional distribution. That's a reasonable notion of correlation. Yeah. I don't mean correlation as vectors or anything like that. This is some probabilistic version, but like maybe I don't understand.
So can the adversary choose xt plus 1 such that the correlation is minimized?
The adversary can do whatever he wants. In particular, he can choose independent data if he wants. You just don't have a priori. You don't have a promise on what he does. That's it. Like in some sense, the bad adversaries in the adversarial setting should be correlating the data, because like in some sense that is the bad case.
Minimize the
that maximizes the regret of. I see what you're saying. Maybe like the thing is, like you're saying, oh, if there's correlation, give condition on xt, you have information about xt plus 1, but that's not how you should see it. It is how much does xt, the distribution of xt plus 1 change depending on the actions you have done. We can talk about it offline, but the thing is, like you should think of correlation not. It's not a priori correlation, it's a posteriori correlation. So, but we can talk about it. But I understand your question, I think, but it's a longer call. Are there any other questions? Okay. So, I mean, just to finish that comment, like think of the tree example, right? In the tree example, the next two things that come up or you're tested on depend on the example you've seen so far. But even given the example you've seen, so you still don't have information about those two. But the distribution of those two does depend on the thing that you've seen so far. That's what I mean by correlation. Like, so it's like, does that help? Yes. Okay. Okay. So we'll talk about something called the smooth adversary model, which is a model that we want to study, which tries to interpolate between the two cases, and hopefully we'll get again maybe best of both worlds. The setup is actually very similar. I mean, it's exactly the same up to some minor changes. There's a learner, and again now there's an adversary who picks an xt adversarially. But we want to think of the adversary as being slightly restricted in the following sense. At each time, there is some noise that gets added to the xt by nature, let's say, because of like reasons of the real world, and that's the thing that you need to predict on. So you receive xt plus noise, and then the adversary, the learner predicts y hat t, which is the label, and the game goes as before. And the quantity that you are Measuring is the same as before. It's again there's expectations before the summations. It's the number of mistakes that you make versus the number of mistakes that the best hypothesis makes on the realized data, which is x hat t plus eta t. So this is the quantity that you need to, yes.
One of the terms coming from the distribution.
Which of the terms?
Those two terms, XG and this.
Yeah. So eta t comes from some noise distribution. This thing.
There's a distribution.
There's some distribution for the noise. XT prime is the adversarial setting, and there's some noise added to the thing. I mean, morally, this is like supposed to be similar to say Spielman and Tank's smooth analysis. There's some arbitrary instance, and then there's some noise added to this arbitrary instance, and then you're solving the problem on this slightly perturbed setting.
So the adversary gets to choose xt, and eta t is chosen by
nature or yeah. And then you get tested on when the hindsight optimal gets tested on x hat t plus each time. Yeah, I mean you can make some relaxations, but for now let's think of it as being fixed on some.
So basically, eta t is the major contributor.
That's correct. So that's what I mean by you interpolate between the two settings. You'll have some parameter corresponding to how much noise there is, and you'll get like some regret bound that is hopefully behaves well with respect to this this noise term. Therefore, you'll get some interpolation of the regret between the worst case setting and the average case setting. And you're totally right. If eta t is like significantly larger than what xt contributes, you are predicting on eta t, and that's the same as that it is in that sense we are interpolating between the two. Are there any other questions? So okay, just to make sure that this captures some intuition that we had before, the instances get slightly perturbed by noise, and this is again in the same spirit as Spielman and Tank's smooth analysis is supposed to capture noise inherent in nature and finite precision and things like that. And the adversary is otherwise arbitrary. So eta t is arbitrary. Xt is arbitrary. X hat t is arbitrary, which is supposed it can, for example, it can depend on the entire history so far. It can depend on the noise so far as well, everything you've seen so far, the whole transcript so far. So it does again try to capture the correlations across time steps, and the thing that you're predicting on is it dependent on the past. So there's some state case.
The noise distribution,
well, now let's think of it as no to the algorithm. Maybe we can get back to For now, think of this as Gaussian noise or something like that. For now, as a motivating example.
So each time step is the same distribution, or
for now you can think of it as the same distribution. You can make changes with changing and all that. It does not change too much technically, and
if I'm given samples of the form of x, can I learn that distribution?
So yeah, that's a good question. We can the question is what regret you would get. We can talk about it often. It's actually an interesting question. The thing is, you just don't need to. You shouldn't be. If you try to learn the whole distribution, you'll have dependence on the domain size and things like that, right? And which is so far we saw no regret bounds that depend on the domain size, so you don't want dependence of that sort. You only want to be able to learn the distribution with respect to the class. Now the question is, when you have adversarial perturbations, can you we actually will talk about a model that sort of captures this whole thing, and it's a slightly more abstract setting, and then we can talk about what exactly there. It's actually more clear what the question is, and we can talk about it. Okay, so to somehow capture this had many unspecified things that what the noise distribution is, what do you need to assume about the noise distribution, and so on. So we want to capture this using a more general setting, and this is something called, or what we call smooth distributions. This is the thing that it's supposed to capture is that the distribution of xt does not put too much mass around any one fixed point. Again, this is similar to the motivation of Spielman and Teng for their original smooth analysis. So what? How is this captured? So there's a base measure mu, which usually is a uniform measure on some set, which is fixed beforehand. Now let's say no for now, and the distribution is said to be sigma smooth if its density with respect to the base measure mu is bounded by some quantity, which is 1 over sigma, which is the parameter which we'll sort of try to. This is an interpolating parameter. Uh, which captures the adversarialness of the data. And what we have is that the density with respect to this base measure is bounded by 1 over sigma. Does that make sense? Are there any questions? This is sort of the main.
For discrete distributions.
For the discrete distribution, the most natural thing to take would be so sigma would be the base measure to be the, let's say, the uniform measure on some set, and would mean that the point mass, like the probability that xt equals x, would be bounded by 1 over sigma times like maybe the domain. Yes.
So basically, just trying to understand this. So if sigma is high, it means the variation is quite low.
If sigma is high, the variation is quite low.
So sigma, what does it correspond to? Is it anything close to standard deviation?
I mean, philosophically, it's supposed to be like standard deviation. This does not mean directly. It directly is not, but like, for example, if you have Gaussian noise, the sigma would correspond to standard deviation. If Gaussian noise on like on like Euclidean data, it would correspond to standard deviation.
And this does not capture discrete, right?
No, it does. Actually, discrete is the one that captures more readily. Because for discrete, you will have like, I mean, d mu by dt sounds very real and like real. I mean, this quantity, this ad Nikodym derivative would just correspond to the probability mass function. It's very fancy way of writing it.
So the PMF itself is bounded.
The PMF is bounded. Does that make sense? So just to sort of fully specify the model that we are interested in, the thing that we'll study is the following thing. At each time your data is drawn from dt, which is a distribution, and the adversary picks this distribution. Condition like fixing, like having looked at all the past data, and the only constraint is this dt by d mu, which is bounded by some number 1 over sigma. And as before, you predict and you measure the loss of the player minus the loss of the best in hindsight.
So what is the condition? Like, does this imply some condition on the noise variable itself? For example, if noise is uniform, does it give you a good DT?
Yeah. So it actually is a little bit more general than. So the reason why this is why this and not directly study noise is that we don't want to have results. At least conceptually, don't want to have results that depend too much on what the noise model is. Somehow that is also brittle to like, you don't want to say something that is it's very specific to your noise model, and it's a little difficult to come up with a noise model that simultaneously works for the. So in the learning setting, usually you don't even talk about the structure of the domain X. Somehow you want to simultaneously capture when it's Euclidean and when it's discrete, like without even specifying what X is, as long as it's reasonable. And for that reason, you don't want to say something about explicit about noise. You don't want to say it's Gaussian. You don't want to say it's uniform or something like that because of this reason. But you're right in the sense on the discrete space, if you sort of take a point and add some uniform noise around the point, this would lead to this definition with appropriate parameters. But the easiest thing to see, at least in this notation, is if you take a point mass and add Gaussian noise to it, this will have bounded density that's proportional to the standard deviation. This is a true fact. Does that make sense? Okay. Is the model clear? This is the model we'll be talking about. So this is.
So everything is captured within DT. So adversary and noise, everything captured.
Yes, everything is captured in DT. Yeah. The DT is just the distribution of what you'll predict on at time t. Okay. So the question we want to address is what the complexity of smooth online learning is. And firstly, we look at the statistical aspect. Sigma is infinity or something. Oh, sigma is 0, yeah, right. Yeah. The that's good. So this captures the this is the same thing, same issue which I think you brought up, which is whether mu is like in this, at least what we're talking about so far, we're talking about mu known, as in like mu is some fixed measure that you know already. The stochastic prediction problem is interesting even in that case. Actually, the complexity we get is like not easy mentioned some other thing, but anyway, it's interesting in that case as well. And as you send sigma to 1 or something like that, it captures that problem. When mu is unknown, it's a longer discussion. We can talk about it. It's a more interesting question, but like maybe for the rest of the talk, we won't focus on it. Does that make sense? But at least you agree with sigma to 1. This is the same as IID data from mu, right? Yes.
For the stochastic setting, that derivative would be.
Yeah. So the annoyance I think which Kiran was bringing up is that this mu, whether this mu is known or not. So the stochastic, the full like the pack setting. Usually the way people talk about is the data is IID from an unknown distribution. It's also interesting to talk about the prediction when data is from a known distribution. Like for example, a lot of Boolean learning happens with the uniform distribution or something like that. But strictly speaking, like the VC theory is for like unknown distribution. So that is what Kiran was bringing up, I think, is my understanding. And yeah, so that's the annoyance. Yeah. So you're right in the sense it does capture. If you set sigma to 1, it does capture the data is IID, but from a known distribution. Did I misrepresent your question? Okay. So what's the complexity of online learning statistically? Okay. So the min-max statistical rate for this problem is what we want to understand. So recall that in the stochastic setting, the regret is a square root t times the VC dimension of f. And in the result in box 21 or something like that, we show that for any class and the sigma smooth adversary, we have the regret is bounded by the VC dimension of the class, square root t, and the log 1 over sigma. So in some sense, it's you get an interpolation between the worst case and the average case. With like mild dependence on sigma, but like now you have like the dependence on f is very nice. It's VC dimension, which is again supposed to be small. Are there any questions about what the rates are? Yes.
So the above regret is an expected regret, but this is a worst case regret.
So okay.
Worst case expected.
So even this is worst case expected, and so what it depends on what your worst case expected means. That's maybe I should not have been like sloppy about this, but like without worrying too much, you can okay. So it's easier to think about expected regret, but without much effort for these rates, you can get high probability regret as well. For like square root t, you can just apply like Azuma hefting or something like that, and you'll get high probability regret as well. Now, but the worst case is over distributions, fixed distribution, and like you take the worst case. And if I tell you the distribution as well, you'll get this rate. Like in the, so it's worst case expected in that sense. And that's exactly the sense in which this is also. So,
the reason I asked is because you mentioned average case somewhere. So.
Oh yeah, sorry, I meant like average case is average. Like this regret is average case in the following sense that the thing that you're predicting on is average, right? Like it's average case, like data is drawn IID, right? Like so. That's the sense in which, but is the quantification clear like this? Worst case over problem parameters, but expectation over the transcript of the protocol. But again, without much effort, you can go to high probability. Are there any other questions?
Data hides log p factors.
So it hides log of the things that are inside. So log p, log 1 over sigma, and maybe log this. Any other questions? I think we can remove the log t by itself. Any other questions? Yeah, so these rates match the stochastic setting up to logarithmic dependence on the smoothness parameter, and that's okay. Okay, so we quickly, so I have about 10 minutes, right?
Yeah, we can go for 20.
Or 20 minutes, okay. But maybe I should quickly go. I'll quickly go over the proof and talk to me offline if this was a little too fast because there's another part that I want to go over. We'll firstly the warm-up case, which is non-adaptive adversaries, which is sort of easy, and this tells us at least the main technical challenges, and then maybe we can quickly see what the technical fix is. Just to recall, in the stochastic case, empirical risk minimization will give you the correct answer. So you can look at the data you have seen so far till today, just fit the best model and predict it for tomorrow, and that will give you the right rate. But this does not work even if you had the following. The data D1 to, so there are different distributions, D1 to DT, but they're fixed beforehand. So the xi's are statistically independent, but they come from different distributions. Even in this case, your ERM does not work. You can't just fit your model to the data you've seen so far. You have to be more clever than that. Okay. So just to again recall the expert setting, which is what this is a generalization of. When you have n experts, so that you have n different models that you think one of them is correct, and you want to predict using their help. There are algorithms that give you a regret that is like square root t times log n. So the issue here is that f is infinite, so there are infinitely many experts. So you're trying to predict with the prediction of one of these f's. So it's like the n expert setting where n is like maybe like really larger, infinite. Does that make sense? Cool. So what do you do? The most natural thing to do is approximate f with a finite class. So what's the finite class that you should think of? The class that is most natural is that if the probability under mu, which is the base measure, the f disagrees with its proxy in its like finite like subclass is smaller than epsilon. Epsilon is a parameter which we can try to fit later. Okay, this is great. What you do? Then you can just run your favorite online learning algorithm on this finite subclass, and you get regret that is like square root t times log f. But importantly, with respect to the best hypothesis in f prime, not the best hypothesis in f. That's what the regret guarantee would be. So this is okay up to this issue that you're only getting regret with respect to best hypothesis in f prime. The hope is that somehow this is enough, and so this is a cartoon picture of what's happening. You have f, you sort of approximate with f prime, and then you get like appropriate regret. And you need to sort of talk about the approximation error, which is the max number of points that fall in the gaps between what your actual thing and the f proxy that you're taking. Now, like, how do you bound the difference in these two things? So so what do you basically need to bound? You need to bound this empirical process, which is the expectation of xi from di max over the elements in the hypothesis class, minimize over the elements in the proxy class, and the number of times f and f prime disagree. This is some empirical process. And we also note that because of smoothness, you have that the expectation of the inner summit is bounded by some number, epsilon times 1 over sigma. Right? Yes.
Do we assume existence of f prime, or are we going to find it?
Yeah. So, okay. For now, let's say we'll find it. But the thing is, when you have fixed measures, these things are known to exist. There are covering numbers for VC classes. There's something called Hausler's bound. But we'll talk about the existence. But now, for now, assume that such an f prime exists. Okay. So, but the point is, the reason why it's all easy for non-adaptive adversaries is that for non-adaptive adversaries, all the xi's are independent, even though they come from different distributions, they're independent. And you can just apply some slight generalization of the VC theorem. If the bound actually looks scary, it's not super important. But the point is, it depends only on the VC dimension. That's the so this quantity is bounded by square root t times the VC dimension. This is this is not like, I mean, this is like the some reasonable application of the VC thing. Does that make sense?
So this is already order T, so it's not.
Oh no, so there's an epsilon in front of the order T. I get to pick epsilon. Yes.
How large is this prime D?
Also, f prime will have size 1 over epsilon to the d. 1 over epsilon to the VC dimension. Yeah. So log of that is like VC dimension times 1 over log 1 over epsilon. So I mean, the challenge is going to be like not the size of f prime. It's going to be this process for the adaptive case. So if like the point is that you can just set epsilon. In this case, you can just set epsilon to be like to kill all these terms appropriately, and you'll get square root t regret. And that's like you'll get like square root log f prime, and that's going to be t times VC dimension times log 1 over epsilon. And this is where you get like log t terms maybe because they're setting actually 1 over t. So this is all like supposed to be straightforward. Straightforward in the sense that you can apply like techniques that just work for ID data. But the main challenge for adaptive adversaries is that because DI depends on the data so far, XI are no longer independent. So you can't just do like standard things like symmetrization and like apply this. And so not ID independent, they're not ID. So this bound needs like, I mean, what you'll do is you'll apply hafting and then apply some union bound, and you need to, even that is not that easy. What you need to do is you need to do symmetrization, and for symmetrization you fundamentally need so you're familiar with symmetrization, right? You take the test point, train point, and then swap them, and you'll get some Rademacher series, and you bound that Rademacher series. But to do that, you somehow it's really important that they're independent, and that's why you used it. So in particular, you can just think of if they were not independent, the theorem is false, or as stated, this theorem is false.
But there are these
there are learning algorithms that for this binary prediction problem, you'll get like, so you can, there's a corresponding process like this which you can bound, but like by default you'll get, instead of VC theorem, VC dimension, you'll get Yellowstone dimension. Actually, even that is not stated, but like you'll get something of that sort, and that is too large. That's what we don't want to. So basically, anything that like as we like, when you have dependent data, there is a notion of symmetrization, something called sequential symmetrization. But instead of like Rademacher random variables, it becomes worst case over all martingales or something. It's some very, very crazy thing to bound, and that usually is bounded by Yellowstone dimension, not VC. Any other questions? Yeah. So you can't just apply VC theorem. So the point is that you need to bound an empirical process of this form. The empirical process is you have a function class with functions that are low expectation under the base measure. Let's say the functions are all positive, and you have x1 to x3 generated from an adaptive sequence of smooth distributions, and you need to bound the expected max of the sum of Gi. This is the empirical process that you need to bound. This is very analogous to an empirical process you bound for learning, the usual learning theory, but X would be independent. Now you have that generated from an adaptive sequence of smooth distributions. Okay, so here's the main sort of technical lemma. This is actually not very difficult to prove, but it somehow makes all of this very simple. What we'll show is that an adaptive sequence of smooth random variables can be simulated using a larger set of IID random variables. In particular, we show that for an adaptively chosen set of smooth distributions, d1 to dt, there is a coupling between draws from di and draws from id from mu, which is the base measure, such that with high probability, xi is contained, like set contained, like it draws xi set contained in z1 to zkt with high probability, like with high probability. And here we think of like k as like roughly 1 over sigma. That's the lemma. Yes. As like this is some set of numbers, and this is some other set of numbers, and I'm just saying contained as in like.
Basically, there are subset of these.
This is like x1 to x, from each one, like there's x1, x2, x3, xt. That's some set. Take that set, and this z1 to zkt, some other set, and I just mean set theoretical, and there's nothing fancy. Any other question?
Like there is a subsequence in the that's the same distribution.
Morally, that is that's a subsequent, but there's some. The reason I'm writing this way is that you need to worry about what that like subsequence is, what is that measurable with respect to, and things like that. So actually, yeah, like, but like think about it that way. There's a like if you draw like xkt random variables, there's a after looking at the random variables, I can pick a subsequence such that if I just tell you the subsequence, that would be distributed according to it's like something like that. But like then you have to throw away, like you see why it's annoying. Say it that way, right? So the coupling thing is easier to. There's some conditional independence and all you have to worry about, but let's worry about that later. Is the lemma clear? Okay. So actually, with this, it's not very hard to see how to prove this now. The idea is sort of simple now because these are positive random variables. I'll just apply the coupling lemma. We know then with high probability that x1 to xkt or x1 to xt are contained in x1 to xkt. So that's a larger set. So if I add more numbers, that number is only going to be larger. But those things are IID. And now I can just apply the VC theorem from before and then apply the VC theorem from before, and you'll get like the bound that we want. So
the regret bound will get is.
No, so actually, like that's not fair, right? Because this quantity is only there in the analysis. Z1 to zkt is not even there in the the transcript of the protocol does not even have Z1 to zkt. What it has is only x1 to xkt. Like this is some empirical process that you just so happen to come up in the analysis. My claim is that this empirical process is bounded by that empirical process. That's a purely mathematical statement. It has nothing to do with like the game regret or anything like that. Yes.
Can you go to the previous slide? So this is kind of surprising because Z1 to ZKT are actually just numbers, and we are saying that all the Xi is a subset of those numbers.
These are also numbers.
Yeah, but drawn from possibly infinite.
Yeah, that's correct.
So are we saying X1 will correspond to Z1 to Z1T, Z1K? Sorry.
X1 to Z1K. Oh yeah, I mean you can make that happen, yeah. But these are IID, so you can reorder them however you want.
Okay, I'd like to see the.
It's actually very easy. It's a good exercise. But we can talk about it. But like the point is, it's actually not very difficult. It does sound very implausible, but it's fairly straightforward once you decide to prove it. Somehow the pointers. Okay, we'll get to it later. Does that make sense? Okay, cool. That's the proof. Maybe I went a little fast, but we can talk about it offline. It's cute, I think. Okay. So in recalling the regret bound that we get is square root t times log 1 over sigma times VC dimension. This resolves some open problems from about 10 years ago, about almost exactly the same setting. They asked whether what was the smooth complexity of online learning, and this essentially the full proof we saw resolves the problem from like cold 10. In particular, what this shows is that smooth online learning is approximately the same as stochastic learning. Any other questions? We'll switch gears and go to a slightly different setting and then slightly different aspect of the same setting and then So if there are questions about the statistical setting, this is a good time, or like after the. Okay, perfect. I think I should be able to. Okay, so the next question that we want to address is the complexity of like the computational complexity of smooth online learning. And here's the framework in which we want to think about computational complexity. The main driving question is, can we algorithmically reduce sequential decision making to offline decision making, which corresponds to optimization. So can we reduce sequential decision making to optimization? That's the main driving thing. And one way to capture this is the Oracle efficiency model, where we are asked to design efficient algorithms for sequential decision making, where you are given an oracle corresponding to the stochastic problem, which corresponds to empirical risk minimization, which is the oracle takes as axis x1 to xi, yi, t in any data set, and it outputs the best hypothesis in the class for this data set. That's what the oracle does. This is interesting when the set of hypotheses is large, but the underlying space has combinatorial structure. The prototypical typical example for this is optimization algorithms such as like shortest paths on a graph. The set of like the hypotheses or the set of things that you're optimizing over is exponentially large, but you have efficient optimization algorithms for this set. The unfortunate thing is that the decision making is objectively harder than optimization in the sense that even given an Oracle access to ERM, you cannot you can show strong low bounds saying that you can't achieve regret regret in the setting. So optimization is easy. Okay, decision making is harder than optimization in that sense. Are there any other questions? Any questions? And yeah, these are like strong strong query complexity low bounds. Okay, so we can ask what happens when you have a smoothness, and the reason why this is interesting is the original motivation for smooth analysis from Spielman and Teng was to understand running times of algorithms. Most famously, the simplex algorithm, and somehow smooth analysis is supposed to give you more efficient algorithms. So you can ask whether smooth analysis in this case gives you efficient algorithms where there are none known to be possible. And what we show in that work with Eka, Janssen, and Kunha, and another independent work by people at MIT, Sasha Rackman's group at MIT, show that you can get regret bounds that again depend only on the VC dimension, but in this Oracle efficiency model for a smooth analysis. Note that the dependence on sigma is a little bit worse, but you can show some computational statistical gaps for this problem, saying that you can't do much better. So this is the okay. Are there any questions about the bound or the setting or like? Okay, so I'll be super brief about the proof. I mean, the idea is sort of simple. Like the syntax of the algorithm is just like it sees a data set at time t, and it has access to this is the data that you're seeing so far. It has access to ERM. The most natural thing to do would be just predict using ERM, and you can show that even for non-adaptive adversaries, this does not give you non-trivial regret bound. So you can't just use ERM. So we need to use the fact that x1 to xt are smooth. And the main idea is that you use a coupling lemma to sort of argue that the uncertainty in the future is captured by samples from mu. This is a bit vague. So maybe the algorithm clarifies what that means. The algorithm is very simple. You pick some hyperparameter n and draw random variables x1, z1 to zn from the base measure mu and add random labels and run ERM with respect to your data set and this made up data set and just predict using that. This is in the same framework. Like this framework is known as FTPL, and this is some version of the FTPL algorithm. But the main challenge is what this n has to be. If n is allowed to be very large, you can actually show that just vanilla FTPL does give you regret. But in the smooth setting, we can show that this n can be taken to be polynomial in like the problem parameters, and that's the interesting. Actually, it turns out you need to take n to be the number n to be random as well, and that's the interesting thing. But we can get to that. And the proof itself is sort of goes through the standard notion called stability, which bounds the loss of your current prediction. So HT is your current prediction at time t. And QT is the distribution of the, like, because you're making a random prediction, it's the distribution of that, and it's a loss of HT on your data today versus the loss of HT plus 1, which is the data that already looks at XT and YT, and the difference between that. Bounding this expectation gives you regret bounds. And what we show is that, sorry if I'm going super fast now, but what this shows is that, the stability term can be bounded in terms of some total variation distance between QT and some average of the future QTs, and some term which is XT and XT prime, which is drawn from the future instance between the two losses. This is like when it's resampled. This is like some generalization. But the first bound we can bound using some information theoretic techniques, because this sort of looks like some point versus mixture hypothesis testing, and we can show some. It's analogous to showing low bounds for like point versus mixture hypothesis testing. And the second bound, again, we can use something like the coupling lemma to show that the second bound is second term is bounded. This is something that we call modified generalization. So, in summary, just to recall, the algorithm requires the bound that we get is square root t times some polynomial term in the smoothness parameter times VC dimension. And also note that the oracles that we call depend only on the are called only on sort of average case inputs, because we sample from mu and then run. The reduction does not do anything crazy. And also turns out that this regret bound gives improved regret bounds for the worst case setting when you set sigma appropriately. Like it gets better than no bound for the adversarial online oracle efficient adversarial online learning, which sort of importantly depends on the fact that this use this weird square root inside the square root, but that's a longer story. Yeah, so the moral of the story is that even computationally, smooth online learning has the same complexity as stochastic learning. So the main takeaway is that the smooth adversary model gives you a model for sequential decision making, which captures correlations across time steps and gets you statistical regret bounds interpolating between adversarial and stochastic case, and reduces sequential decision making to optimization. But actually, because of the generality of this coupling lemma idea, you actually get a sort of broad recipe for smooth analysis for these sequential decision making problems. But I'll skip this and talk to me offline if you're interested. And this leads to other applications other than sequential prediction, like sequential decision discrepancy minimization, data-driven algorithm design, and certain problems in sequential, like solving sequential games. In conclusion, we saw the smooth adversary model, which captures, which gives better than worst case bounds for both statistical and computational aspects of sequential decision. I'll take any more questions. And thanks for running. Thanks for staying, and sorry if I ran over time. Yeah, the mu in the algorithm is the same mu as the coupling lemma. So, like, huh?
So, what mu is? Do you need this D1 to D2?
So, like when you, at least in the framework that we talked for the most class, most of the lecture, we assume, let's say, mu is known, because again, in the discrete case, you're thinking of it as like the uniform distribution on the domain, or in the real case, you're thinking of it as the Gaussian or something like that. When mu is unknown, it's an interesting question. It's actually more subtle. Everything I said like does not go through as I said, so that's a different that we can talk about. But like, let's say mu is known for now.
Sorry, I missed one of the parts. What does the oracle provide in the second?
In the oracle takes as input data set, which is labeled samples xt, yt. and it gives you the best hypothesis on that data set, which is maybe it's too far to go back, but it just gives you argument of it gives you that quantity, which is our best hypothesis in class. That on the data set, like that
And
prediction.
you can ask it for any of.
You can ask it for literally anything, but the complexity, like the running time, depends on how many things that you ask. Like you can't ask exponentially. I mean, you can ask exponentially many, like x1 to xt, then you'll be running in exponential time because you still need to write that down.
Go to the slide title recipe for smooth down.
Oh, okay, okay. Yeah.
I think sorry. Next slide.
Huh?
Oh no, it's the
Oh.
end.
Oh. This one?
Yeah.
Okay.
So I think you made some points about this bound being leads to improved regret bounds for. So can you talk a bit more about it? So what was the
Okay.
previous one?
So what is the in the adversarial setting where like data is literally arbitrary? For the Oracle efficient model, you had a sorry.
Was it a reduced to dimension?
Oh no. So I mean, you could get VC dimension bound, but like you'd get like so before what the bound you had was square root t times absolute value of the domain size. That's what was known before. This is Daskalakis and Sarkanis. If you set sigma is mod sigma is like domain size, you'll get like a improved like you'll get a better parameterized bound than yes.
The idea of the efficient algorithm is that you in each time you query the oracle just once with a filter.
Yeah, that's correct.
And for the non-efficient case where you had log of sigma.
Uh-huh.
So, like, are you querying the oracle more?
So in the inefficient setting, like where you had this log regret, I wasn't even thinking about it in this Oracle efficiency model. I was even like you can do whatever you want. Like your algorithm can do arbitrary things. It doesn't even have Oracle access. It's not restricted to run in polynomial time or anything like that. It can do arbitrary things, and turns out like what the algorithm does is that it does take this covering or like this approximation f prime and runs some inefficient algorithm on that, like runs multiplicative weights on that set, and which runs in like polynomial in the thing in the cover size, but that's exponential in problem parameters. You discretize the set and then run hedge on it, hedge or like whatever on it. But that's going to be the discretization is going to be exponential size.
So a couple of questions. So first regarding what I had asked before, Z1 to ZKT.
Mm-hmm.
So if there is a subset that is I mean, if you're saying the samples that you get are a subset of that, that means that Z1 to ZKT might have almost full measure.
I mean, Z1 to ZKT are like points, like I don't understand. So I mean, okay, it's very important to notice the following. I mean, I'm saying there exists a coupling. So I'm not saying this is independent of this or anything like that. That's like false. So I mean, in particular, it can't be independent of this because of this property. So there's some joint distribution between this and this, but these are independent. But there's some joint distribution between this and this.
And Z1 to ZKT, you choose points. Okay, do you choose points Z1 to ZKT?
No, they're drawn ID from like think of this as a distribution. Okay, actually maybe. Okay, I'll wait for if anyone else has questions. Then we can. I can just tell you. I mean, we can like this thing.
Yeah, we can take it up.
Yeah.
There's one more question. Like from all of your analysis, is there? Do you see any further work that might come out of this, say for specific distributions?
So one question that is interesting is this like the Oracle efficient setting, you get this like 1 over like sigma, like this dependence instead of log 1 over sigma. We have some lower bounds for some parameters of sigma. We don't have full lower bounds, and it is plausible that maybe there is some choices of parameters where you actually may be able to get like, okay, actually there is like follow-up work that shows that for specific classes, for like half spaces in let's say d dimensions, you can actually get efficient algorithms that get logarithmic dependence on sigma. They were interested in some applications in robotics or something like that, and they thought this is a good model, and then they gave some Oracle efficient. This is Max Simchowitz and Adam Block at MIT. They showed for some generalized like half spaces or like and mixtures of like affine combinations of half spaces. They show that you can get like logarithmic regret, but like so understanding for what classes you can get logarithmic regret efficiently is very interesting.
And there are no classes of no assumptions that you can make that get rid of that incident.
So I mean it has to depend something on the class, I guess. So VC dimension is like, okay, so the VC dimension is a lie. So it's not really VC dimension. What you have is something like the covering number of the class under the measure mu. It's upper bounded by the VC dimension. So you can get like that parameterized quantity. Even if you want to even like, okay, very interesting question is there's a constrained class of distributions, which is that mu thingy, like set of things that are density bounded by 1 over sigma with respect to mu. And then there is this hypothesis class. What is the joint complexity of this this problem is a good question. This does not like fully answer this. It answers it in a min-max sense, but you can ask it in like some fully parameterized sense or something like that, and that would be interesting. I don't fully know the answer to that question. But this does answer it in the min-max sense, as in this hypothesis. Yes.
I have a basic question. So, like, can I state the problem in a way that in each round it's an expert setting, and the adversary in each round has to choose one of the distributions from the k distribution,
Right.
and the distribution has a constraint that you define. So, like an extension to the expert setting is that you have set up a family of functions that in each round you get a cost function. So, like, would that be an interesting, like a cost function but with some noise?
Yeah, you can do that. So the convex settings are usually easier than this. Like one of the challenges is that the fact that the 0-1 loss is not convex. So that does lead to some annoyance. But it like I don't see at least any conceptual reason why studying analogs of this for like the expert setting is not interesting. That is, people study versions of this even when you have d fixed distributions and getting regret with respect to this to get like something analogous to this multi-distribution learning. This is a paper by Nika and like one of the students that corresponds to this problem, and like they study it in that setting. There are many different extensions one could study, and I think we can chat offline. Are there any other questions?
Okay, if there are no more questions, I'd like to call upon Professor Chandan to hand over a token of appreciation for this.
This was the